let's talk about some properties that carry over and talk about how to represent them symbolically. You guys are going from just crunching numbers to representing things symbolically in math. And eventually, if you keep going in math, you're going to learn how to really prove stuff. In linear algebra, you do some proofs. And prerequisite to that, you have to know how to express this stuff symbolically. So scalar multiplication, let's say we have a vector, and let's say the vector is v, and it's represented with components v1, so v subscript 1, v2, v3. And if we need a vector u, we'll represent it u1, u2, u3. So scalar multiplication, do you think that's going to be exactly the same as it was in the plane? Symbolically, actually symbolically and geometrically. So if I were to take v and multiply it by a scalar, remember a scalar is just a real number, right? It could be a variable real number, but it's just a real number as opposed to a vector. So let's use c for our scalar. Then in component form, what would c times v look like, you guys?
C times v1. C times v2.
Yeah, I mean, how else are you going to do it, right? Whoops, got to put that c in there. How else would you do it? And that physically, that has the same effect. If c is a positive number, for instance, bigger than 1, then c times v is going to be c times as long as v, and it will point in the same direction as v. If c is negative, then it points in the opposite direction. Addition, subtraction. Okay. So if we take another vector u with the same sorts of components except u1, u2, and u3, then symbolically, what would u plus v look like? What would the first component look like? u1 plus v1. And then same thing, except the subscripts will change with each position that you move over. So u2 plus v2 for the second component, and u3 plus v3 for the third component. I mean, how else are you going to do it, right? And if you've ever added matrices together, then you do it the same way with matrices, right? A matrix is a rectangular array of numbers. So really, I'll tell you a secret, a vector can be thought of as a matrix, a certain type of matrix. And so you add corresponding components, just like you add corresponding elements or entries in a matrix. Oh, by the way, is it going to change much if it's subtraction? So we could list it, I think, all in one if we use a red a symbol for subtraction. Does that make sense? Okay, the triangle law. Well, the triangle law is just a way to add vectors, right? So the only thing I want to say here is the triangle law holds. And if you think about it, it makes sense because any two vectors in space lie in a plane, right? So there's no reason why the triangle law for the plane wouldn't extend to vectors in space because they lie in their own plane. What does the triangle law say? Well, if you have a vector, let's put it there. Let's call that u. And let's say you have a vector, I don't know, v that looks like that. Then if you want to add u plus v visually, then one way to do it is to do what? Yeah, attach the tail of v to the tip of u. If you want to write it in the order u plus v, of course, you could do it the other order, and that would technically represent v plus u, but it'll be the same value. And then what do you do to get your what's called a resultant vector? In general, that connect the tail of the first vector to the tip of the second vector, and that vector in purple, I'll put v in another place. That vector in purple would be u plus v. Of course, I drew it in the plane, but the idea is that there's no reason why this wouldn't hold in space because u and v lie in a plane somewhere, right? By the way, you could make a parallelogram out of this too, couldn't you? You could put another copy Actually, I'll do it in a really slick way. I'll just go Control-C, Control-C, Control-V. You could put another copy of V at the tail of U, like so, and then another copy of U opposite the first copy, and there you go. There's your parallelogram. And then U plus V is the diagonal of the parallelogram.
That's pretty redundant.
Some books do call it the parallelogram law. Now realize the other diagonal of the parallelogram will be a different value, which we'll talk about what it could be later on. Okay, magnitude of a vector. What do I mean when I say use this symbolism? Now, you might see double bars, you might see single bars. It means the same thing. If it's single bars, from the context, you know that if it's a vector inside the bars, it's not absolute value, it's magnitude. So what does that mean symbolically? What do we do to find the magnitude? That's what this symbolism means. What do we do? What formula do we use to find the magnitude of this vector, essentially? We actually have a name for that formula. Isn't it just the Pythagorean theorem in space? It really is. Or the distance formula in space, if you think about it, because the origin is 0, 0, 0. So that would be the square root of V1 squared plus V2 squared plus V3 squared. It's the same formula as in the plane, we just have an extra component added in there that's being squared, right? Or an extra value, it's not a component, it's a scalar value, V3, that's being squared. Oh, that should be, say a 3 right there. There we go. Now it actually makes sense, which is always nice. Okay, number 5, C stands for a scalar number, and the magnitude of C times V, what can we do with that C? If you've watched the video, I probably went over this in the video as well.
Pull out C absolute value.
Yeah, we have to, in case it's negative, we have to make it absolute value because if you think about it, when you apply the magnitude formula to C times V1, C times V2, C times V3, if C is negative, when you square the individual components, the negative goes away. So to take that into account, we pull out the C, but if C happens to be negative, it's important to have absolute values around it. If C is positive, it's still true. It's just not as important because absolute value of C is going to be equal to C when C is positive. So long story short, the magnitude of C times V is the absolute value of C times the magnitude of V. And then a really important concept, we can get a unit vector, a vector that's 1 unit long from any vector. Do you remember what the formula was? So what would be the unit, what would be a vector that points in the same direction as V, but is 1 unit long?
1 over magnitude times that vector.
Yep, that's true. And then we usually write it as V divided by the magnitude of V. But what does division mean when you're talking, what does scalar division mean? Well, it really means scalar multiplication, right? 1 over magnitude of V times V. So the first way you said it is really the best way to think about it. But of course we get lazy and we want to write less symbols. So we say V divided by the magnitude of V is a vector that's 1 unit long.